The exercises for today will be on two numerical computing topics, pseudorandom number generation and automatic differentiation. Let's jump into the first problem. We're asked to look at this sequence 3 times 2 to the n mod 11 as n goes from 1 to, let's say, 100. And the idea is that this sequence of numbers is supposed to mimic a sequence of random numbers from 1 to 10. So each number should be independent from the previous ones, and you would like for this sequence to have some properties in common with a random sequence. And in some ways it does. So let's program it. We can start by putting the first entry into a vector and then repeatedly adding a new entry. So for from 2 to 100, we will push onto this list twice the last entry, and then we should mod that by 11. And the reason we're doing it this way rather than just using, say, a list comprehension is that if you compute 2 to the n for each value of n, then for one thing it's computationally inefficient because you're having to repeatedly raise 2 to higher powers, but also it's going to overflow. Once you get past 2 to the 63, you're not going to be able to represent these numbers as 64-bit integers, and you're actually going to get a bunch of zeros. So what we do instead is we double each time. If you think about what's going on inside the parentheses here, as you increase n, you're just doubling inside here each time. And you can mod by 11 on each step rather than waiting to do it at the end. So in some ways this sort of looks like a random sequence. There's not any particularly obvious pattern to the eye, but we should subject it to a more strenuous test than that. So one simple thing we can do is just do a tally using the countMap function from StatsBase. And we find that every number appears exactly 10 times. And that's a bit suspicious. If you do a tally using the built-in random number generator, 100 numbers from 1 to 10, then you get some variation. One number appears 16 times, another number appears as few as 6 times. Most of them are kind of around 10. This behavior is a bit suspicious. But anyway, it certainly passes the test of not being too heavily skewed towards one number or another. But we would like our random number sequence to do more than just kind of spread out evenly across the numbers, because you can imagine just doing 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and then starting over again. And certainly if you run that sequence for a long time, the numbers are going to be well represented, but it's nothing like random. So as an example of something a little bit less obvious to look for, we can check for each pair of consecutive entries starting from an odd indexed one and then getting the even indexed one right after it, how many times it happens that the next one is actually smaller than the one before it. So the even indexed one is smaller than the odd indexed one right before it. So what we're going to do is sum up these Boolean values where we check is a2i less than a2i minus 1, and just see how many there are. And there should be 50 total comparisons being made here because we have a length 100 sequence and we're blocking it up into subsequences of length 2. And it turns out that actually 40 of them have the property that the second entry was smaller than the first one. Furthermore, the other 10 are all greater than. So actually it never happens that 2 consecutive entries are equal. And that is not a property of a real sequence of random numbers. You would sometimes generate a 4 and then another 4 right after it, or a 7 and then a 7 right after it. And that's not happening with this sequence. So that's a number of failures that this sequence has as a random number generator. And if you subject the built-in random number generator to the same tests, it's going to do much better. In the second problem, we're looking at the golden ratio, so 1 plus square root of 5 over 2. That's a special number. And we're being asked to look at the fractional part of successive powers of that number. So if we look at the number itself, which is built into Julia, it's like 1.618, so the fractional part would be this 0.618 stuff. We can compute that by doing mod of the number with respect to 1. And what we're being asked to look at here is the fractional part of successive powers of phi. And we're being asked to investigate whether that's a reasonable pseudorandom number generator for the distribution that's uniform between 0 and 1. So we can raise it to successive powers using the list comprehension. And it turns out we're going to need a lot of precision here. So we're going to use big number arithmetic, and we're going to set precision very high. And actually, even with that, let's just look at the first 30 terms. So if we just compute them, it's unreadable because it's printing huge amounts of precision each time. So let's plot it instead. And in the graph here, what we see is that actually after the first few powers of phi, the fractional part is jumping very close to 1 and also very close to 0 and alternating between the two. So we're actually not getting any numbers here in between. All the numbers are either close to 0 or close to 1. So it might be easier to look at with a scatter plot. So you can see, other than at the beginning, everything is very close to 0 or very close to 1. So this actually related to a very interesting math identity that allows you to compute the Fibonacci numbers in terms of powers of phi. But for our purposes here, the main thing we need to notice is that the numbers are not spreading out nicely at all. And another way to visualize this is to look at a histogram of these values with, let's say, I don't know, 12 bins. And there's a few things in the middle that's from the very beginning, but then most of the numbers are close to 0 or close to 1. And these bars should be more sort of straight across if the random number generator is going to be reasonable. So to see an example of something that's better, let's just look at multiples of pi. So the fractional parts of multiples of pi, and it's much more reasonable. You get values in the middle, towards the ends as well. We're just looking at 30 here. We could boost this up and look at more, and you can see that it's pretty evenly distributed. There's sort of roughly 30 of each bin here. So the second part today is about automatic differentiation. And the idea of automatic differentiation is that if you have a large computational system, so a function that's defined by a lot of code, and you want to differentiate it, what do? The reason you might want to differentiate a function like that is if it represents some loss function, so it specifies how good or bad a particular model is at fitting some given data. You might want to perform some gradient descent on that loss function. In other words, move in the direction where that function is decreasing most rapidly to try to get it down to some small reasonable number. And at that point, you will declare victory and use that set of parameters that you found for your model. So if you have a function and you want to differentiate it, the classic thing to do is just the thing you learned when you took single variable calculus, which is follow some differentiation rules. You can do this in Julia using the Python library SymPy, and the way it works is you use this vars macro to declare a symbol, and then you use the diff function to just differentiate. So we plug that symbol into this function, and that's going to produce just a symbolic representation of the function. And we can differentiate that, and it performs the same calculation you would perform in a calculus class. And we can substitute x equals 2 into that, and the way that substitution works in the Julia SymPy library is we use this pair object, x, and then this thick arrow, and then the value that we want to actually substitute. And we're going to convert this to a float 64. If you want to see it without the float 64, we can see the answer is exactly 6 over e. So that's a result of a symbolic calculation. But we can also turn it into a float 64, and we see that the answer is around 2.207. By the way, this operator here is what's called a pipe operator, and it's just a shorthand for this operation. So it forwards whatever's to the left as an argument to the function on the right, and it's just a way of organizing the flow of data in a bit different way. So the problem with symbolic differentiation as a tool for solving machine learning problems is that expressions get out of hand very quickly. For example, here's a simple function that we're calling g, and it takes a parameter n, and if n is 1, it returns x. If n is bigger than 1, then it calls itself recursively. And if we want to see what happens when we apply 6 recursion levels, it gets pretty big. There's this large expression here that's being managed under the hood by SymPy, and this gets out of control very quickly. You really need to be able to reduce down to some numbers at each step in order to be able to keep the problem from ballooning out of control. So one straightforward approach to this is to just evaluate the function at 2 nearby points, subtract and divide. So in other words, use the definition of a derivative and make a finite approximation of that. And the problem with this approach is that it's not very accurate. So let's investigate it in this case. What we see is that when k is very small, so the h value is 2 to the minus 60, for example, then we just get zeros here. And the reason for that is for such a small value of k, 2 plus 2 to that value of k is not going to be distinguishable from 2 using float 64s. So these two values are going to be exactly the same as each other. They'll subtract to give 0, and then it doesn't matter what you divide by at that point. It's just all going to be zeros. And then later in the sequence, it's reasonably accurate, but let's look at the accuracy for real. So we had this float 64 value up here. Here we go. What we find is that the best we get is about 10 to the minus 8 in terms of accuracy. And machine precision is 2 to the minus 52, which is about 10 to the minus 15. And so actually we lost about half our digits of precision. We should be getting about 15 accurate digits, and we actually only got about 8. And the problem here is that when you subtract f of x from f of x plus h, catastrophic cancellation is occurring. When you subtract two nearby values, the condition number of that operation is very large, because even though the error isn't being magnified in a subtraction operation, the relative error is being magnified because the new number is going to be much smaller than the original numbers f of x and f of x plus h, typically. So this is going to be a common situation. You lose about half your digits of precision every time you perform one of these finite difference operations to try to approximate a derivative. And that's going to be catastrophic if you have to do this a lot, because you only have 15 or 16 digits of accuracy to begin with. You lose half of them the first time, half of them again the second time. All of a sudden you're down with just a couple of these operations, you're down to just a few digits of accuracy. And there needs to be a better way forward. Unfortunately, there is. It's called autodiff, or automatic differentiation. Conceptually, the idea is that symbolic differentiation involves retaining the entire function at every step of the operation. If you plug a symbolic variable x in, that allows you to see the whole expression for the function, and you're actually finding the derivatives everywhere at the same time. And then at the end, you make a substitution and only find the derivative at a single point. So this is wasteful because it's keeping track of what's happening everywhere instead of just what's happening at the single point where you really want the derivative. Difference quotients gives away too much. It only keeps track of the function's value at two specific nearby points. And autodiff strikes a perfect balance between those two extremes. So instead of keeping up with just one piece of information, the function's value, or all the information, what the function is doing everywhere, we keep track of just two pieces of information. One is the function's value, and the other is the derivative of the function at that point. So in other words, we're retaining the first two terms of the Taylor series, the value and the derivative. And one of the underrated aspects of the chain rule is that it tells you that a derivative of a composition depends only on the derivatives of the functions. So we don't need to keep track of any higher order information. We can always calculate derivatives based on knowledge of derivatives of the constituent parts. Same for the product rule and for the linearity of the derivative, which says how derivatives behave with respect to addition. So this is going to be a mathematically viable approach. Instead of throwing away everything but just the value at the point we're interested in, we're going to retain the value as well as the slope there. So the way this works in Julia is we define a new object called a dual number. And struct is the Julia keyword for defining a new type. And it's going to have two parts, a value which represents the value of the function that this dual number is representing, and then the derivative part which represents, of course, the derivative. So for example, if we have a function that knows how to interact with these dual number objects, we can plug in a dual number like 2, 1, which represents the value 2 with a slope of 1. Symbolically, that's corresponding to x at x equals 2, because the identity function x has a slope of 1. So you can always think of a function f as a composition of the function f with the identity. And dual number of x, 1 represents the identity function evaluated at x. So the disadvantage of this approach is we do have to tell our system a lot of things. We have to tell every basic function that f might interact with how it's supposed to treat this new object called a dual number. So let's take that approach here for the same function that we handled above. So we said we want to evaluate f on the dual number 2, 1. So let's just go ahead and try that. It won't work, but we'll see what it's telling us is going wrong. So it says, there's no method matching exponentiation for a dual number with an integer. So we need to define that. And Julia actually has a built-in function called base.power by squaring, which bootstraps from the multiplication operator to an exponentiation operator. And it's called by squaring because that's the most computationally efficient way to multiply numbers in order to raise them to positive integer power. So like if you wanted to compute 2 to the 64, you would start with 2 and square it repeatedly rather than actually multiplying 63 times starting from 2. That means we also need to tell the system how to multiply dual numbers. And remember that dual numbers represent a small window of the function. So the values represent the function's values, and the derivatives represent the slopes of the functions there. So we're really asking, how do you multiply two functions here? And that's going to be the product rule. So we get a new dual number whose value is just the product of the values. And then the derivative is going to be given by the product rule. So we're going to do x dot derivative times y dot value plus y dot derivative times x dot value. So let's try that. And it's going to tell us we have to import the asterisk in order to extend it. So that the asterisk is the multiplication operator. That's part of base. And it's just kind of protecting it a little bit, saying, you know, you need to be intentional if you're going to import this thing. So let's import the asterisk and the exponent. And we find there's no method telling us how to negate a dual number. So we're going to add that as well. We also need to be able to subtract and add dual numbers. And notice that we can bootstrap subtraction from addition and negation. We realize we also need to be able to divide. Finally, we need to tell the computer how to exponentiate a dual number. So the value is just going to be the exponential of the value. But then the derivative is going to be the derivative of the exponential function, which is just itself, times the derivative of the function on the inside. So finally, we have the result when we substitute 2 into this function f. We have the function's value coming out, and we also have the derivative value as well. And we can compare this derivative to the value we got from symbolic differentiation. And what we find is that it's exactly the same, even at the level of bits, all the way out to the end. So there's no additional error associated with using this approach. This isn't the exact mathematical value, but it's as close as you can get in the float64 system. And the finite difference approach we tried lost about half of these bits of precision.